Hi and welcome back to Podcast School. This is an AS Technology and Design podcast. Today we're going to be looking at the SR flip-flop, and that continues the section on electronic systems. If you're following this through from your syllabus, this is Unit 1.20 of the SIA revised syllabus, and this is version 1.1 of this podcast. Now, I said we're going to look at the SR flip-flop, and what I would say straight away is, if you haven't already done so, download the PDF, the notes version of this podcast. Make sure you have that, because this is one of those topics that is a little bit confusing, and if you don't have notes or something to scribble on, sometimes this just won't make sense. So download the PDF and follow this along with me. Okay, so I've said here that a set reset can be built from a pair of cross-connected NAND gates, and you can see that the fact that the output Q is connected back or fed back to the to the other input of the other NAND gate, and similarly Q, what we've called Q bar, is fed back to the input of the other. I've said here that the arrangement is used in logical circuits to remember and retain its logical state even after the controlling input signal or signals have been removed. Now, you probably won't know what that means if this is the first time you've listened to the podcast. I'm going to explain that in just a second, okay? The inputs are generally designated as S and R for set and reset. We've already said that. Now, I've put a little note here, which really at AS level I don't want you to worry about too much, but it's just here for completeness. I've said that the inputs are considered to be inverted in this circuit because the NAND inputs must be normally logic 1 to avoid affecting the latching action, and that's why the inputs are labelled S bar. There's a little bar over here, and R bar. Okay, so if you're wondering why that's not just S and R, it's because of this reason, and to be honest, don't worry about it too much at this point. Okay, so let's have a look at this circuit in more detail here. From now on, if you see the inputs or an output as being red, that means that there's actually a high or a 1 on that input. Okay, if you see it being blue, then you know that it's a 0. Okay, now this arrangement with the inputs S bar and R bar both being 1 can give you this this output where the top NAND gate is a 0 and its output is fed back in, and you know that a 0 and a 1 into a NAND gate will always give you a 1 output, so that becomes a 1, and a 1 and a 1 will give you a 0, and so forth and so on. So that's stable in that state. Okay, there's another possible resting position, and this seems a bit odd or a bit weird because you're always used to, or we've been used to logic at this point having a very well defined set of outputs, but this isn't the case here. There's another resting state, and if you have a think about this, if S bar and R bar are both 1, and let's just say the input to this top one, the lower input is a 0. Well, a 0 and a 1 give you a 1, and that output is brought down and fed back into the lower NAND. A 1 and a 1, well, that will give you a 0, and a 0 out, obviously 0, 1, and a 1 output, and so forth and so on. Okay, so that makes perfect sense, as does this. So you can see that there's two actual versions of output whenever the set and the reset are both 1. It's a bit of an odd one, and the reason for that is something called a race condition. And what a race condition means is it's basically it'll settle into one of those states depending upon which input came first or which output came first. If you imagine this wire were extremely long, okay, and this connection were extremely short, well then you would understand that this input would reach this NAND gate before this longer one would. Okay, and that will have a consequence. Similarly, if it was the other way around, it may have this consequence. In other words, it's a race. It's a race for outputs to settle and inputs to settle. And there is to two alternative outcomes to this race, and these are those. These are the outputs, or these are the alternatives. But that's only when the set and the reset both equal 1. Okay, if you want to read more about race conditions, I've put a link in the notes, which if you go back to the website, you can have a straight through link to it. Okay, I'll also just mention it at the end. Okay, but those, it's important that you realize that those two outputs are valid. Now, taking one of them, so I took the one on the left, we have inputs of 1 and a 1. On the top NAND gate, we have an output of a 0. And because of that 0, then we have an output in the lower one of a 1, okay, and so forth and so on. But what I want to do right now is to show you what happens when S bar is given a low pulse, a negative pulse. Okay, so let's just have a look at the diagram on the right. At the moment there's nothing on there, okay, but if I do this, then you can see that S bar is a 1, that corresponds to that one. Q is a 0, there we go. Q bar is a 1, there we are, and R bar is a 1. Okay, now you may, after I do this, okay, you may want to just rewind slightly and watch this again, because it happens quite quickly, but I'll just do it now and you can see what happens. Just watch this top input. There's going to be a negative pulse here between what I've called T0 and T1, which could be a short period of time. And I want you to see what happens to the outputs Q and Q bar. At the moment, Q is a 0 and Q bar is a 1, but watch what happens. Okay, did you get it? What you should have noticed is S bar went momentarily low, so you saw a blue input here for a short period of time. And the knock-on effect is Q was 0, it's now a 1, denoted by the red. Because that's a because that's a 1 and a 1, then our output Q bar has also changed from a 1, which it was previously, to T0, which it has now changed to a low, the blue line. Okay, so it's gone down. In other words, Q has changed from a 0 to a 1, and Q bar has changed from a 1 to a 0. And, well, needless to say, R bar didn't change, so it's constantly a 1. Alright, so what is the point of that, you might think? Well, really, what it is it's a latch. If you notice that S bar went momentarily low, it was a low pulse, it could have been a very short period of time. That event, if you like, was caught by, well, both Q and Q bar. They changed, they flipped over. Notice even after S bar went back to a 1, well, Q and Q bar stayed Q as a high and Q bar as a 1. Okay, and in fact, if you look back at the previous slide, these are the outputs. These are the other outputs, the alternative outputs that I mentioned just a second ago. But in any case, Q and Q bar have latched or have remembered the fact that S bar went low. Okay, and that really is the whole point of these flip-flops. Okay, again, rewind this and have a look at the animation again, just to prove to yourself that that's what happened. Okay, so let's have a look at this again, just in another format. You can see what I've done this time is I've added the timing diagrams in as little snippets into the input S bar and the outputs Q and Q bar. Okay, and what we'd looked at was this scenario from before, but you can also see that if in the other situation, when Q and Q bar were initially the opposite, so instead of being a 0 it was a 1, and instead of being Q bar being a 1 it was a 0, then you can see the outputs after the pulse. In fact, in this case, you can see that the pulse made absolutely no difference, and Q stayed as a high and Q bar stayed as a low. Okay. Similarly, if you have a negative pulse on the reset input, you will see that these two alternatives will be both valid. Okay. the output here is a 0 on Q, and the output on Q bar is a 1, given in a low input pulse on R bar. And in this situation, Q, the output is travels to 0. It is a negative falling edge, or falling edge rather, should I say. And Q bar has a rising edge, given a negative pulse on R bar. And what I would really urge you to do is just to take a piece of paper and just to prove to yourself that those indeed happen. Okay, so lastly then, let's just sum this all up. This is the truth table for an SR flip-flop. And you can see that a 0 and a 0 provide no change. A 0 and a 1 will give outputs of a 0 and a 1. Okay, depending on, given well, you can look at it two ways. Given a 0 negative pulse, or sorry, given a negative pulse on S bar, or a positive pulse on R bar. Alright, a 1 and a 1, I've said, is unstable, and that produces a race condition. And I've already spoke a little bit about that. Again, you can see a link to some more information on that on the website. A 1 and a 0 will give Q as being a 1 and Q bar being a 0. And something I should have said just before now is that Q and Q bar are always the opposite each other. In fact, the proper term for that is Q bar is the complementary or the complement of Q. They're always opposite. Okay, now I've written some text there. I'll not take time in this podcast just to read it through to you, but again, take the notes and have a look at it and convince yourself that that truth table is in fact valid. Okay, now I do understand that that is a quick run through, so again, please rewind and check out that the operation is true, and you will need a piece of paper and a pencil or a pen to check that out. And then lastly, I've left you with the references. These are just in here for completeness. You will find a clickable link in the podcast. Okay, that's it for now. Whew, that was a tough one. I hope you've understood. What we'll try and do later on is get some exam questions on this stuff, and it might actually put it in context a little bit more. Okay, until next time then. See ya.